Good evening. Welcome to the Museum of Science. I'm James Wetzel, the co-producer of Adult Programs, and I am so honored and pleased to introduce you to tonight's Reno Family Foundation Symposium, Extraterrestrial Life. I am so honored to be welcoming our special guest for the evening, joining us all the way from Harvard University. Of course, I'm referring to the incredible Dr. Avi Loeb. Among Dr. Loeb's many credentials, he is the chair of the Department of Astronomy at Harvard University. He is also the founding director of the Black Hole Initiative, and we are just so pleased to have him here tonight on the stage. Over the past year or so, he has become a leading voice in the conversation about our first known interstellar visitor, also known as Oumuamua. And we're going to hear about all of that tonight and so much more. He has a great presentation for you all. And towards the end of the evening, we will have a time to answer as many of your questions as we possibly can. Hopefully you saw this slide behind me. This is how you can submit your questions for Dr. Loeb. You can go on your smartphones and go to slido.com and enter the code Avi Loeb, all lowercase, and submit as many questions as you'd like. We'll try and get through as many of those as we can a little bit later on. And following the formal presentation, we invite you to keep the night going. Join us downstairs in the Blue Wing for a dessert reception with a cash bar and continue the conversation with us. Before I bring out our special guests, I have to thank two very important people without whom tonight would not be possible. That, of course, is Jack and Susie Reno. For over a decade now, they have continued to support the Adult Programming Initiative here at the Museum of Science, and without their support and their contributions, programs like this evening and guests like Dr. Loeb would not be able to be on the stages here. So please join me in giving a very, very big hand to Jack and Susie. Thank you. We look forward to many more collaborations. And tonight is a part of our fall season of adult programming. There's still a lot to come over the next couple of months. You can pick up our mailer on your way out and sign up for our mailing list. Those are the best ways to stay up to date on everything happening here at the museum for adults like yourself. But for now, please join me in welcoming to the stage our guest tonight, Dr. Avi Loeb.
Thank you very much, James. It's a great pleasure to be here. Today I'll discuss one of the most exciting questions in science, perhaps the most exciting. But I should start with a confession. Some of us are not sure yet that there is intelligent life here on Earth. But that may be an even better reason to look for it up there. And so the fundamental question is, are we alone? And of course, either answer to this question, yes or no, will have deep implications as to our responsibility for the future. And I should mention that a week ago, the Nobel Prize in Physics was awarded to two astronomers, Michel Mayor and Didier Queloz, who discovered the first planet around a sun-like star. And if we imagine life out there, the first thing to think about is a planet like the Earth around a star like the sun. Before we go out to the street, we look at our image in the mirror, and that's the perception we have of what we might see on the street. It's not a bad perception, but that's what is natural for us to assume. And so finding planets around other stars is the first step in the search for life. And the third person who received the Nobel Prize was for the development, that was Jim Peebles, for the development of our current model of the universe, how the universe started from the Big Bang. And of course, beyond asking the question of whether we are alone, there is the question of when did life start, if not only on planet Earth, where else, and how soon, how early, and what will happen to it in the future. For the young people in the audience, that's an important question. Now, many of us tend to think that we are at the center of the universe. Humanity as a whole believe that, and a number of religions believe that the Earth is at the center. Philosophers argued for that, Aristotle, for example. And everything centers on us. The physical universe is centered around us. Turned out to be a wrong perception of reality. We are not at the center of anything. The Earth is moving around the sun, And when Galileo suggested that, he was put in house arrest. That didn't change the facts, which is an important lesson that science is not about getting more likes on Twitter. It's about evidence. Clearly, Galileo did not get a lot of likes at the time, but it didn't change the truth that he was advocating. And Copernicus was the one to recognize first that the sun is the center of the solar system. Now, even though we realize that the Earth moves around the sun moves around the center of the Milky Way galaxy. And the Milky Way galaxy is drifting in some random direction. That is an important lesson that we are not at the center of the physical universe, but many of my colleagues still believe that we play an important role, that we are at the center of the living universe. Perhaps we are special, perhaps we are alone, we are unique. And various people raise a number of important arguments in this context, why the Earth is rare and why life on Earth, the way we see it, is special and unique. But I can fully understand this tendency of feeling special by viewing my own daughters when they were young. They tended to think that everything centers on them. And as time went on, they went out to the street and they found other people that look similar. And they realized that those people have qualities that may be even better than theirs. And so they developed a sense of modesty as a result. And they matured. And as a civilization, we are following the same path. We tend to think that everything centers on us. That's natural because at first you realize things happening around you. So you think, oh, well, it must be related to me. You might even think that there is a divine entity that controls everything that happens to you. And then you realize that you're not really center stage, that there are lots of other things happening around you. And so, as a civilization, we would recognize that we are not also at the center of the living universe, in my view. That we are not special in any way. And that's what I try to advocate to my students, freshman students at Harvard. They come with high self-esteem, and I try to say that by looking at the sky, you should develop a sense of modesty. Because there are more planets like the Earth in the observable volume of the universe than there are grains of sand on all beaches on Earth. And moreover, we live just for 1% of a millionth of the age of the universe. So how dare we be arrogant? That makes no sense. But if you look at the history of humans, you find emperors or kings that boasted after conquering a piece of land on Earth. Since there are so many Earths out there, the situation is similar to an ant hugging a single grain of sand on the landscape of a huge beach. Nothing to be proud of. It's quite actually, it's quite ridiculous for an emperor or a king to be proud of himself. And usually these were alpha males, as you can see from the previous image. But to me, the more interesting question, it seems quite obvious that we are not special and that we should develop a sense of cosmic modesty. But the second question that arises, if we are not special, are we the smartest kid on the block? That's what my girls try to figure out. And if I had to guess, I would say probably not. The Earth formed life out of the ingredients that existed on Earth by some random processes. And if you open a cookbook, you realize that out of the same ingredients, you can make very different cakes, depending on how you mix these ingredients together, in what order, how much heat you apply to them, and so forth. And so you can imagine other Earths producing different types of life. And I have no pretension to believe that life on Earth is optimal in any way, especially if you open the newspaper, you see the politics of the day, and you realize it could have been better, right? And so there might be cakes that were baked to taste better out there, and creatures that are much more intelligent than we are, or simply had more time to think about things and correct themselves, and perhaps develop technologies that will take us a while to recognize. And so it would be worthwhile to try and meet them and learn about them. But what's most important is to be open-minded, not to have a prejudice, not believe that we know the answer before we actually look through our telescopes. That's the mistake that philosophers made in the days of Galileo. Some of them refused to look through his telescope. They said, we don't need it, we know the truth. And unfortunately, some scientists say the same nowadays. They believe they know the answer before actually collecting evidence. And my point is quite simple. Let's collect the evidence first. Science is about evidence. And let's not have prejudice. In other words, whatever technology we have in our hands right now, let's use it in order to explore this question. And this question is of great interest to the public. But most of my colleagues put it aside as outside of the mainstream of astronomy. And frankly, I don't fully understand that, because if the public is interested, and you are a testimony to that fact, and if the public is funding science, how dare the scientists say this is a question we don't want to address? Now, they do that because they believe that it may actually look non-professional, since there is all this literature of science fiction and there are reports that are not standing up to the level of scientific scrutiny about unidentified flying objects. But that doesn't mean that we should retreat to a position where we don't explore this question, where just ignoring this question is a sin to science, because this is a fundamental question about the universe, and we have the technology to explore it. So how can we avoid addressing it? It's much more relevant to society than many other questions that scientists address, such as the nature of the dark matter, or extra dimensions, or the multiverse, things that will never be observed and are considered part of the mainstream, even though we will perhaps never get data to test these ideas. So instead of looking at the mirror and trying to guess what the answer is, maybe we should go out to the cosmic street and, just like my girls did, figure out if we are the smartest kid on the block. And in starting the search, we should start nearest to us, of course, in our backyard. Now, of course, one way to start the search is to do experiments trying to create synthetic life in the laboratory. And there is a group here at Harvard that does that, led by Jack Szostak, a Nobel laureate. And of course, if we create synthetic life in the laboratory, that serves an important role of guiding us as to where to look, because we can recognize whether there is only one recipe for making life, the recipe that was developed by the Earth, or maybe there are many multiple paths to developing life, and we can figure out which conditions could lead to life, and therefore search for environments that support these conditions. So that's one way to do it, and in fact, physics developed this way. We first did experiments in the laboratory and then went out to the universe. And lo and behold, we found that the same laws of physics that we discovered in the laboratory hold on large scales and describe the universe as a whole, which was remarkable. I mean, there is no reason why the universe should be organized in the same way that we discover in the laboratory. There are lots of laws that try to tell people how to behave, and people don't behave the same way. So laws that prescribe human behaviors do not necessarily hold. Why would the laws of physics hold? If we discover them in our labs, why should they hold on the biggest scales? But they do. The universe is organized, and in fact, that is the most remarkable fact, I think, about the universe, that it pretty much obeys the same laws as we find in the laboratory. So we can explore the living universe the same way, starting with laboratory experiments. But beyond that, we can start to search in our backyard. And so the closest detector to us is the Earth's atmosphere. And an object that would come, let's say, from outside the solar system and cross the atmosphere of the Earth, it could burn up. These are called meteors. And if they're big enough, more than a meter in size, then they leave behind a meteorite. Now, all the meteors that were reported until recently were originated in the solar system. But about a year ago, I was invited to an interview in a radio station about a meteor that was discovered above the Bering Sea off the shore of Kamchatka in Russia. And in educating myself about meteors, I went online and I found this table of all the meteors that tabulates all the data on meteors over the past 30 years. And that data was collected by US government sensors that are used for national security. You can imagine what they're used for, but they also record meteors passing through the atmosphere of a natural origin, not human-made objects. And so I asked an undergraduate student that works with me, and by the way, I like young people because they don't carry a baggage of prejudice. They are not attached to their egos as much as my senior colleagues. And they're willing to explore without a prejudice. So I work with undergrads as well, and one of them is Amir Siraj, and I told him, look, there is this data set from the US government. Why don't we check if there is any meteor that may have originated from outside the solar system by extrapolating its orbit and seeing if it's bound to the sun. If it's not bound to the sun, it originated from outside the solar system. And he went on, and we found one such object that was discovered in 2014. And this is the first meteor that was recognized as potentially being from outside the solar system. The only problem was that the US government released information about its speed when it impacted the Earth, but did not provide error bars. And the reason they didn't provide error bars, in my view, is because they were very small. Obviously, for national security, the detectors need to be very good. But we're still in the process now of the paper that we wrote being reviewed. And the interesting point is that some referees objected, saying that they don't believe the US government, and therefore, they cannot, if there are no error bars reported, they will not accept the paper for publication. But the editor of the journal, the Astrophysical Journal Letters, found an innovative way of approaching this issue by having a reviewer that has security clearance that could look behind the fence and check if indeed the data is reliable. So we're still waiting for the verdict on that, but at least without the error bars, it looks like this object came from outside the solar system, and it's really the first documented object that originated outside the solar system. And frankly, if such an object leaves behind a meteorite or something, this is our only chance of putting our hands on a piece of technology that came from outside the solar system, from another civilization. Because it would land somewhere. If we figure that it's interstellar in origin, we can then go to that site and examine whatever fell. So that's an interesting window towards what's going on outside the solar system. We have to remind ourselves that actually going places, going to another star, takes a long time. If you use the current rockets that we have and you want to reach the nearest star, it will take 100,000 years, the nearest star. So that's roughly the amount of time that elapsed since the first humans left Africa. So if you wanted to reach the nearest star now, you had to send a spacecraft when the first humans left Africa. It will only reach it now. Now, the next place where we can search is the moon. Now, why is the moon interesting? For two reasons. One, the moon doesn't have an atmosphere. So anything that impacts the moon will not burn up, it will just land on the surface. And that's why the moon has so many craters, because everything falls on it. Nothing burns up in an atmosphere surrounding it. And so, in principle, you can look at the surface of the moon and search for material that came from outside the solar system. And you can do so by identifying isotopes that imply that the material did not come from the solar system. You can find the isotope ratio that is indicative of material different from the material that made the solar system. But moreover, the moon also doesn't have geological activity. The Earth, the surface of the Earth, gets turned around within 100 million years. So if there was another, for example, human species that was around 100 million years ago and had computer terminals and everything, it's all buried now inside the Earth. We will not find it in archaeological digs. But the moon does not have geological activity. Nothing turns around and gets mixed. And so whatever landed on the surface over the past few billion years is still there. And all we need is to establish a base and excavate, have archaeological sites on the moon. And the moon acted as a fishing net that collected whatever landed on it. So it's sort of like a mailbox that collects mail that was posted in our direction. If we never check that mail, we would never know that we received a message. And perhaps the message is, we exist. You know, maybe there is something that crashed on the surface that is technological in origin. Maybe there is some biological stuff that came from another planetary system. We should just check. And NASA initiated the program Artemis, aimed at establishing a base on the moon beyond the year 2024. So this would be an interesting scientific goal to pursue on the surface of the moon. Then if we go beyond that, we can monitor objects that enter the solar system from outside. And the first reported object was Oumuamua. And you can see the trajectory that it went through in the year 2017. So it was at closest approach to the sun on September 9th. But we discovered it only on September 19th, after it already passed that point. So it was sort of like having a guest for dinner at home, and then you noticed that guest late in the evening, and this guest looked very weird. But by the time you realize that, the guest left out of the front door into the dark alley, and you can't really find it anymore. And that's the experience we had with Oumuamua. Now, I follow the same practice as I do with everything, all my research. So a year ago, when there was a report about hydrogen being much colder than we expect in the early universe, I suggested maybe the dark matter has a little bit of electric charge, a small electric charge that would cool the hydrogen early on. That was a hypothesis that we published in prestigious journals like Nature magazine or Physical Review Letters, and there was not much fuss around it. Here, in the case of Oumuamua, there were a lot of unusual properties that were identified. So I followed the same practice and tried to analyze them and make the most reasonable sense out of them. But for some reason, it got a lot of attention. And so let me explain why this object was so unusual. So first of all, we didn't expect it to come. I mean, so a decade ago, we wrote a paper where we estimated the abundance of interstellar objects, and we didn't expect anything to be detected with the Pan-STARRS telescope that detected Oumuamua. It's a telescope, a survey telescope in Hawaii that monitored the sky and looked for Earth-crossing asteroids, those that are dangerous. We would like to know about any object that may hit the Earth because we don't want to suffer the same fate as the dinosaurs, right? So we want to protect ourselves. And so this telescope was monitoring the sky and found this object where we expected none to be found. But more interestingly, this object actually was at rest in the frame of reference of the local population of stars. So if you take all the stars in the vicinity of the sun and you average their random motion, you get to the so-called local standard of rest. And this object was at rest in that frame, sort of like a buoy sitting on the surface of the ocean at rest, and then a ship runs into it, that ship being the solar system. So we ran into it. And that's a very unlikely situation. Moreover, when we monitored its brightness, this object tumbled every 8 hours. And its brightness changed by a factor of 10. Now, this object reflects sunlight. So that means that projected on the sky, the area that the object has changes over 8 hours by a factor of 10, meaning that it's either a very elongated cigar, as depicted on the left here, with an axis ratio of order 1 to 10, or it's a pancake. And actually, if you analyze the tumbling motion, you recognize that a pancake is a more likely configuration. So that's quite unusual because all the objects that we have seen before that came from the solar system, asteroids and comets, were at most with an axis ratio of 1 to 3. This one was 1 to 10 or more. You realize that even if you had a paper-thin object, in projection, you would think that it has some thickness because you never see it edge on. Now, moreover, this object did not emit any heat. The Spitzer Space Telescope had extensive observation, didn't detect any heat from it, meaning that it was relatively small and very shiny. It was at the upper end of the reflectivity that we see from asteroids or comets. And it was the size of tens of meters to 100, 200 meters. We don't know exactly how big. And finally, most intriguingly, it deviated from an orbit shaped only by the sun's gravity. Now, we see this phenomena with comets. They are being pushed by the rocket effect of gases evaporating from their surface as a result of heating from sunlight. But then you see a cometary tail. Usually these are dust particles, water molecules that you see coming off the surface of the comet. In this case, there was a deviation, meaning that there was some push exerted on this object, but there was no cometary tail. We couldn't see any water molecules, no carbon-based molecules, no dust, to a very significant upper limit. So in fact, orders of magnitude below what we see for comets usually, and as a result of deep observations with the Spitzer Space Telescope. So we see the object deviating from its orbit, there is a push on it, but we don't see the standard cometary tail, and then the question is, what is pushing on it? So I tried to think about it, and the only thing that made sense is perhaps the sunlight itself reflecting off it is giving it an extra push. But then you infer that if it's indeed a pancake-shaped object, it has to be very thin. So it could be a sail, a light sail. And in fact, we are trying to develop this technology nowadays, and I'll mention it in a few minutes. You can imagine a sail being pushed by light. And for space journeys, that seems to be a very useful technology because you don't carry the fuel with you. And so we just made a suggestion in a paragraph in that paper saying perhaps it's artificial in origin. And then that paragraph was read on CNN and in an interview and was all over the news. And I really didn't, now the attention from the media I found useful because I try to communicate how we do science. So science, most of the time, is filled with uncertainty because you don't have enough evidence. Now the scientists will try to hide it. They would say, let's close the door, stay in our ivory tower, talk among ourselves, and come out to the public only when we know the answer for sure. Because otherwise, who would believe global warming? Now I say, look at the populist movements these days. They don't believe, some of them don't believe global warming. Why? Because they say that science is an occupation of the elite. Why do they say that? Because we, as scientists, some of us, close ourselves in a room and don't communicate to the public the scientific process. And in fact, most of the time, there are multiple hypotheses put forward. We just don't have enough evidence, so we can't decide which one is right. It's just like a detective story. You have various suspects. The police does it openly, right? So you have various suspects. You try to figure out who is to blame. We should be open about the process. The public should know that we are uncertain, because then we get more credibility. It's not an occupation of the elite. Anyone can understand it. You know, when a plumber comes to fix a pipe in my home, it's a simple process. I look at it and I understand it. The same thing is the scientific process. You know, you have evidence. You're trying to figure out how to solve the puzzle, just like a broken pipe. I mean, there is nothing different fundamentally about it. And frankly, I don't see myself different from the public. I still see myself as the young kid trying to figure out the world, making mistakes, trying to put out conjectures. So what's the problem? You know, we might, some of us might be trying to maintain an elevated image of ourselves in pursuit of honors, awards, public recognition. You know, it's good for our ego. But the scientific process fundamentally is about eliminating uncertainties by evidence, and sometimes being wrong. You know, Einstein was wrong towards the end of his career. He argued that black holes don't exist, gravitational waves don't exist, quantum mechanics has spooky action at a distance, he argued, that makes no sense. He was wrong. Whenever you work on the frontier, you can be wrong. There is a lot of uncertainty. The evidence is not clear. So that's part of the scientific process. Let's not be arrogant. Let's be modest. Once again, modesty is a very good virtue because it allows you to venture in directions that enable discoveries. If you always want to maintain your public image, you don't want to make mistakes, you never venture in those. And frankly, the business world recognizes that fact. So venture capitalists invest in risky propositions. Why do they do that? Because one of these risky propositions may turn out to work, to be profitable, and then it would pay for everything else, for all the other mistakes that are being made. And so in science, it's the same way. We don't know in advance what will bear fruit, and we should allow ourselves to make mistakes. So at any event, the bottom line is this object could be of artificial origin. We just didn't have enough data. Let's continue to look for objects like it. And let's not be afraid to discuss this. I should say that there were a few scientists that tried to explain the same facts in a mainstream way, but even those explanations were extremely exotic. For example, they argue that perhaps Oumuamua is a fluffy object that on average has a density less than the density of air, so that sunlight can push on it. To me, that sounds even more speculative. Imagining cloud of gas being pushed by sunlight of 100 meters in size. How does it maintain its integrity as it rotates every 8 hours? Others suggested that maybe we don't see the gases, the outgassing, because it's made of hydrogen ice, which can easily evaporate at above 15 degrees above absolute zero. So we've never seen a site producing hydrogen ice that survives through a long journey through the interstellar medium. That's also speculative. But we should put all possibilities on the table, and the next visitor, weird visitor that we see coming to our dinner next time around, we should look at it more carefully and not rely on prejudice. Now, there was a second interstellar visitor that was discovered just a month and a half ago by a Russian amateur astronomer. He built a 65-centimeter telescope and was looking in the direction of the sun. You might ask, why would you look in the direction of the sun? Well, that's the place nobody looks at. So he had a chance to discover things that nobody discovers. Another possible reason is that it's the place where you can see the glint from satellites if you want to find satellites. But at any event, he discovered this object that looks like a comet. So this one, which is also interstellar, definitely interstellar, it's moving too fast to be bound to the sun. This one shows a cometary tail. So I was immediately asked, well, if this one shows a cometary tail and it looks as if it's just like a solar system object of natural origin, wouldn't you conclude that Oumuamua was natural? And I said, if you go down the street and you see a weird person, and then that is being followed by a lot of normal people, that doesn't make the first person normal, right? So the fact that we see this object as being a typical comet means that Oumuamua was even more unusual. Why was it so different? And actually, in the first date when I met my wife, she looked special to me, and since then I haven't met anyone like her. So I have a personal reason to think that, meeting an unusual, having an unusual encounter can stick around, Another way to find interstellar objects is by searching for objects that passed very close to Jupiter, for example, and received a kick so that they became bound to the sun after that. The kick originates from the force of gravity exerted on the object as it passes close to Jupiter. And so there should be a collection of objects that were interstellar in origin, passed very close to Jupiter, within a few times the size of Jupiter, and were trapped in the solar system. So in this case, Jupiter and the sun act as a fishing net that collects interstellar objects. And how would you find them? Well, if they're interstellar, they do not lie preferentially in the plane that characterizes the motion of all the planets. All the debris of material from the formation of the solar system occupies a plane because it was made out of a disk of gas that circled the sun and fed the sun, and the debris from it made the planets and the asteroids and everything else. So most of the objects you find that were born in the solar system are in the same plane, especially close to the sun. There were some that were kicked out during the history, but if you find those interstellar objects, they come from random directions, so they have very high inclinations relative to that plane. And that's one way to identify them. Objects that move around in the vicinity of Jupiter and, for example, rotate in the opposite direction to the orbital motion of the planets, or go at a very high inclination relative to the planetary plane. So that's another way, and we estimated how many of those should exist based on the discovery of Oumuamua, and estimated that there should be of order 6,000 of them. So we can look for them, and then the advantage of having them bound to the sun is that we can visit them, we can explore them. more carefully, in difference from Oumuamua that is on its way out, and we can never chase it, we can never reach it with conventional rockets. It's just moving too fast. And also finding it would be really difficult because by now it's extremely dim. So if you were to design a mission that will chase it, it needs to be equipped with a big telescope, and even then it's not clear that you would find it. So potentially, some of these objects could have brought life to the solar system, by the way. They could have transferred life to the solar system. Now, going beyond primitive life, you can ask, what signs of intelligent life can we find out there? And the simplest thing you can look for is artificial light. So an interesting question to ask is, suppose you have a city like Tokyo, far away. How far can you see it with the Hubble Space Telescope? The answer is you can see Tokyo from the edge of the solar system. So with the Hubble Space Telescope. Nobody mentions that because nobody thinks that it's plausible to have a spacecraft which produces as much light as a city of Tokyo, but it's something to keep in mind because maybe one of the lights that we see out there with the Hubble Space Telescope is associated with an artificial origin. How would you find out? Well, if you see an object moving away from us, as its distance increases, there are two possibilities. It will get fainter either because it reflects sunlight, so as it goes farther away, it intercepts less light, so the amount of light impinging on its surface drops as 1 over distance squared, and then the amount of light that we see drops by another factor of 1 over distance squared. So altogether is 1 over distance to the 4th. So objects that reflect sunlight, like asteroids, for example, they become dimmer as they move away from the sun, like 1 over the distance to the 4th power, very quickly. That's why Oumuamua became very dim very quickly. We can't see it anymore. But an object that produces its own light, like a spacecraft or a city, only suffers from 1 factor of 1 over distance squared. So it dims more gradually as it moves away from us. So we can tell the difference between an artificial source of light and an object that simply reflects sunlight. When I asked an astronomer that discovered most of the objects in the Kuiper belt, in the outer solar system, I asked him, did you ever check if any of them dims with distance as it changes its distance from us, whether it dims as 1 over distance to the 4th or 1 over distance squared? He said, why should I check? It's obvious. It must be 1 over distance to the 4th. There is no point in checking. Once again, having a prejudice, in a way, helps you to maintain your image, but perhaps makes you at the same time avoid a major discovery. As I often say, extraordinary conservatism leads to extraordinary ignorance. That's a paraphrase on what Carl Sagan said. He said, extraordinary claims require extraordinary evidence. I don't think so. I think extraordinary claims require as much evidence as ordinary claims. Now, if we now venture outside the solar system, you can see here all the planets, the Earth, and then 10 times farther away is Saturn. 100 times farther away from the sun is where the solar wind meets the interstellar medium. It's called the heliopause. But that's not the edge of the solar system. There is the so-called Oort cloud of objects that were kicked into a sort of spherical shell surrounding the solar system by Jupiter, and they go all the way out to 100,000 times the distance between the Earth and the Sun. Roughly halfway to the nearest star. So the nearest star, if it has an Oort cloud, the 2 Oort clouds are touching each other. The nearest star system is Alpha Centauri. It has 3 stars in it. One of them is a dwarf star called Proxima Centauri, and the other two are stars like the Sun. Most of the stars in the Milky Way galaxy are dwarf stars, just like Proxima Centauri. They are about 1/10 of the mass of the Sun. The Sun is not a typical star. A typical star is Proxima Centauri. And such stars, like Proxima Centauri, live for 1,000 times longer than the Sun. The reason is they're smaller, even though they have less fuel to burn. And by the way, stars are just like nuclear reactors. They burn nuclear fuel, but they're held together by gravity. Nuclear reactors are held together by solid material, you know. But a star is like a nuclear reactor held by gravity. So that's what the Sun is. So these dwarf stars are smaller in size, they have less fuel, but they burn more slowly. So they would last for 1,000 times longer than the Sun. When the Sun dies, we might want to move to a dwarf star like Proxima Centauri, which is next to us right now for the next few million years before it passes away. But there would be another one. Now, a couple of years ago, a planet was found next to Proxima Centauri. It's called PROXIMAB. And amazingly enough, this planet is 20 times closer to the star. So even though the star is fainter than the Sun, it so happens that this planet is much more closer to the furnace, so that the temperature on its surface is roughly the same temperature as we have on Earth. So in principle, liquid water may exist on its surface, and the chemistry of life as we know it. Here is an habitable planet next door to us. And the fundamental question is, does it have liquid water? Does it have an atmosphere? In order to have liquid water, you need an atmosphere. Because solid ice, when you warm it up in vacuum, goes directly into gas phase. In order to make liquid water, you need an external pressure of an atmosphere. So this planet is so close to the star that in fact it always faces the star with the same side. It has a permanent day side and a permanent night side. And my daughter, now she's 14 years old, but a couple of years ago when I told her about this discovery, and I said, look, there is this planet that we can move to when the Sun dies. You know, we might want to go there because the star would live 1,000 times longer, and it has a habitable planet next to it. She said, if we ever move there, I would like to have 2 houses. One in the permanent night side, where I would sleep, and the second one in the permanent sunset strip that separates the night side from the day side, where I would like to have my vacations. And she had this idea when we visited Hawaii, because you know the sunset is beautiful, but imagine having that view for the rest of your life, you know, forever. So real estate value must be very high, and that's for the real estate agents in the audience on this trip. Now, what we can imagine is only life as we know it. In other words, the chemistry of life in liquid water, which requires an atmosphere. And the warning sign comes from Mars. Mars is 1/10 of the mass of the Earth, and it used to have an atmosphere. So it may have had liquid water on its surface. There is some evidence that perhaps it had. But then at some point, early on, it lost its atmosphere, and therefore lost its ability to maintain liquid water on its surface. So we don't see any animals crawling on its surface. That's a warning sign that without an atmosphere, you can't have life as we know it. The interesting question is, does Proxima B have an atmosphere? And there is a simple way to tell. Because if you have bare rock circling the star, the permanent day side will be heated to a high temperature, and we can calculate the temperature contrast between the permanent day side and the permanent night side. The night side will be cold and the day side will be hot. And as the planet moves around the star, we can see the color of it changing with time, periodically. We see more of the illuminated phase as the planet moves at some phases of its orbit, and more of the dark side at some other phases of the orbit, just like with the moon. And so without even resolving the planet, just looking at the light curve during its motion around the star, and by the way, it takes 11 days for it to go around the star, so a year is 11 days, and if there is anyone out there, they celebrate a birthday every 11 days. It's quite, they have a lot of parties. So we can tell whether there is an atmosphere on the planet by comparing what we expect for bare rock to what would happen if you have an atmosphere that moderates the temperature contrast between the day side and the night side. Either an atmosphere or an ocean that would try to equilibrate the temperature contrast between the two sides. We can tell the difference with the upcoming James Webb Space Telescope. We showed that in a paper a few years ago. This telescope is the successor to the Hubble Space Telescope and is expected to be launched in a couple of years, a year and a half. There are other stars nearby that have planets around them, some of which are in the habitable zone. Another dwarf star, so Proxima Centauri is 12% of the mass of the Sun. This one is 8% of the mass of the Sun. It's called TRAPPIST-1, and it has 7 planets, 3 of which are habitable, just like the Earth. And of course, we would like to know. This one is 10 times farther away than Proxima Centauri. We would like to know whether there is life on those planets. Clearly, Earth is our home, but only for a while, because there are many risks that we can imagine. There are internal self-inflicted wounds that we can imagine as a result of not preserving our climate, as a result of nuclear, chemical, or biological war that would eliminate life as we know it. But in addition, there are external threats. An asteroid can impact the Earth. If it's big enough, it could damage prospects for life. There could be solar flares affecting technological equipment. Just 160 years ago, there was the so-called Carrington event that was recorded, and it was a flare from the sun that hit the Earth, and at the time raised the temperature of the atmosphere by a few degrees. But there was no technological infrastructure back then. If it would have happened today, and in fact, a few years ago, there was an event like that that just missed the Earth. If it would have hit the Earth, the damage to the infrastructure of satellites and power grids and so forth would have been in the trillions of dollars. Something that we are not thinking about very often. Now, if we want to venture into space, to move away from the Earth, since currently all our eggs are in one basket, the Earth. If we want to spread the eggs such that, if something bad happens on Earth, we'll still maintain the future of our civilization, we want to go into space. Now, there is an interesting calculation that you can do. Right now, we're on the surface of the Earth. We are held down to Earth with an acceleration, gravitational acceleration of 1g. That's simply the force that keeps us stuck to this auditorium, right? The force that pulls us towards the center of the Earth, 1g. You know that fighter pilots, when they maneuver, they can sustain up to 10g, but that's the maximum acceleration. So it's much more comfortable to feel the acceleration of 1g. And Einstein taught us something very important. He taught us that gravity is not really a force. That in fact, if you were to go on a spacecraft that accelerates, it would feel just like the force of gravity. It doesn't matter if you are accelerating because of an engine or because of gravity. So in fact, if we were to board a spacecraft that accelerates, that increases its speed by 1 g, it would feel just like sitting in this auditorium. Nothing unusual. It would feel very comfortable. Now, if you do that for 1 year, the spacecraft would reach the speed of light. That's a very high speed. That's the highest speed we can reach. If you do that for 25 years, continue to accelerate and get closer and closer to the speed of light, you can traverse the entire universe. How can you do that? The universe is tens of billions of light years in size. It continues to expand. You can do that because of another effect that Einstein recognized. It's called time dilation. The time is ticking more slowly when you approach the speed of light. So within your lifetime, within 25 years or so, you can traverse these billions of light years if you were to continue to accelerate at 1 g. The only problem is there is no such engine that can push you at 1 g for so long, because it needs an amount of fuel that is impossible to range. But this is just a thought experiment. Now, if we are not that ambitious and we want to reach, but nevertheless, we are ambitious and we want to reach the nearest star within our lifetime, what speed do we need to move at? About a fraction of the speed of light. If you want, if you are 57 years old, like myself, you want to do it in 20 years. And that means that you need to move at a fifth of the speed of light, because the nearest star system, for example, Proxima Centauri or the Alpha Centauri system, is about 4 light years away. So moving at a fifth of the speed of light would get you there in 20 years. Can we reach a fifth of the speed of light? Well, rockets carry their own fuel. So they are limited by the speed at which the gas leaves their exhaust. They are based on the same principle as jet planes. You throw material backwards, and that pushes you forward. That's all. That's how rockets operate. When you board a plane in Logan Airport, that's how the plane brings you to your destination. It throws things backwards and moves forward. That's all. Now, the problem with that method is you're pretty much limited by the speed at which you throw things backwards, because you're carrying your fuel with you. So if you throw a lot of fuel and the payload is very small in weight relative to the fuel, you can maybe reach 10 times the speed that the fuel has when it leaves your jet through the exhaust. But that's 30 kilometers per second, which is a percent of the speed of light for conventional rocket fuel. And that's why all the rockets that we launched into space, since Sputnik to New Horizon, always reached that limit of about 30 kilometers per second. Not much has changed since the days of von Braun, because you have to carry the fuel with you. Now, a different technology is a light sail, where you are pushing a very lightweight sail with light, and you leave the fuel behind. And this concept was envisioned by Robert Forward back in the early 60s, soon after the laser was invented. He argued that perhaps you can use very high-power lasers to push on a sail so that it reaches a fraction of the speed of light. And the approach is very similar to the sail of a sailboat, except the sailboat is being propelled by wind, gas molecules bouncing off the surface. In the case of a light sail, it's the particles of light that are reflected off and giving it a push. And since you are reflecting light, you can in principle reach the speed of light. And this is a brief history of myself. I was born in 1962 in a small village in Israel. I used to collect eggs every afternoon. I grew up on a farm. When I was up for tenure at Harvard, I wasn't very worried about it because I always had plan B. I would go back to work in the farm. And frankly, nowadays, I sometimes contemplate that idea because it's a much more relaxing lifestyle to be closer to nature than with some of my colleagues. But at any event, this is me on the tractor with my two sisters. And then we established a family here. I was tenured at Harvard. This is my wife and two daughters. And then one day in May 2015, an entrepreneur from Silicon Valley named Yuri Milner came to my office at Harvard and said, it was a black limousine that parked in front of our building. He came out, and he entered my office. I didn't know what it was about. And then he said, would you be interested in leading a project whose goal is to reach the nearest star within our lifetime? And it didn't take me much time to say yes. Within 6 months, we recognized that indeed the technology of a light sail is the best approach for that purpose, for the reasons that I mentioned before. And we announced this project called Starshot with Stephen Hawking that came for the occasion. So here is an illustration of the concept. The idea is that there is a collection of small, low-power lasers which produce their own beams, and the beams combine to a very powerful laser beam. And then above the atmosphere, there is a mothership that releases a sail. And it's above the atmosphere so that friction with the air would not suppress its motion. And the laser beam is pushing on the sail, which has roughly the weight of a gram or so, and it's equipped with electronics that includes a navigation device, communication device, and a camera, and that can all be packed into 1 gram. We have this technology in our cell phones. And then within a couple of minutes, this 100 gigawatt laser beam pushes the sail of 1 gram to 1/5 of the speed of light. At that point, the sail traveled a distance which is 5 times the distance to the moon. We can focus the light only out to that distance, and then we let the sail continue on a straight trajectory from there in the direction of our target, eventually in the direction, let's say, of PROXIMAB, so that it can take photographs, tell us if the planet has vegetation on the surface, or oceans, or maybe it's a desert, and send those photographs back. And of course, it takes 4 years for the information to get back, so altogether 24 years. It's a long time. But that's the concept we came up with, and the way I view it is as sort of a sketch of what the technology might be like. We have to work on the many challenges that are involved. And that involves developing the photon engine, the light that is pushing on the sail, and then developing a strong enough sail that is very highly reflective, that doesn't absorb much of the light, and worrying about risks from, for example, impact of dust particles. Whenever a dust particle impacts, it's like a small nuclear explosion because this sail is moving at 1/5 of the speed of light. There is a lot of energy being released at every impact. And then, of course, the challenge of communication, which is non-trivial. And finally, I'm told that it's much more challenging to worry about policy issues than about physics, especially when you have a technology that can be used for other purposes. Just to give you an example, a dust grain can cause some damage on the surface of the spacecraft, a crater. But if you coat the electronics with millimeter-thick material, then in principle that would prevent the damage that could be substantial for not allowing the electronics to function. And so our plans are for the next decade to demonstrate the principle by having multiple experimental teams exploring the technologies that are involved. And then if it all looks promising, dedicate the next decade after that to the construction of a prototype, eventually constructing the full system, which could cost as much as the biggest science project that we have, like the Large Hadron Collider. And it will involve funding from federal agencies in addition to private donors. But as of now, Euromilner is committed to fund this first step. In principle, we can imagine that other civilizations developed this technology already. So how can we search for signals related to it? Well, we can look for leakage of the light beam around sails that are launched by other civilizations. So you can imagine, for example, a system that transfers cargoes between an Earth-like planet and a Mars-like planet. So when the two planets align along our line of sight, we would see the beam of light in our direction, the leakage from that. So we can search for flashes of light. And it will be a flash of light because the orientation will be preserved only for a limited amount of time due to the motion of the star, the host star, and our motion. So we will see a flash of light on the sky, and one can search for it. We do see flashes of light in the form of fast radio bursts. The most popular view is that they are associated perhaps with newly born neutron stars. Neutron stars are stars that weigh as much as the sun. They were formed as a result of the collapse of the core of a massive star to a density that is similar to the density of an atomic nucleus. So they have roughly the size of a city like Boston, about 12 kilometers, and the mass of the sun. These are neutron stars. And when they are born, if they possess a very strong magnetic field, they could produce very bright radio bursts. At least that's the conjecture for the origin of fast radio bursts. But we don't know, and perhaps a subset of the fast radio bursts that we discovered over the past decade are due to propulsion systems of the type that I described. You can imagine that advanced civilizations migrated away from their home planets. So, in fact, we send out Voyager 1, Voyager 2, New Horizons that will leave the solar system. And as biological creatures, we are not well suited for space travel. So it's much more natural for us to send technological equipment, electronics, that is designed to withstand the harsh environment of space, being bombarded by cosmic rays and so forth. And so we might, as biological creatures, we might stay on this planet, but we can send out robots that are equipped with artificial intelligence and with 3D printers so that they can produce whatever we want on the target planet out of the raw materials that are there. So if we have, for example, a blueprint for how to produce life as we know it, based on synthetic life that we produce in the laboratory, we can send that information to the system that will use the raw materials on the planet to make life as we know it. We don't need to take precious creatures like our friends and send them into space. There might be some people that would like to do that, just like, in Western movies, you see all these very strange people that are willing to take a risk and die. But there is no reason for that if we have the technology to produce whatever we appreciate here on Earth, to produce it elsewhere. There is no need to send biological creatures out there. And it's quite likely that advanced civilizations, and by the way, if we ever encounter technologies or equipment, even if it's defunct from advanced civilizations, I think it would be shocking for us because it's much more likely to be far more advanced than our technologies. Our technologies are evolving on a 3-year timescale exponentially right now. The car that I'm driving is far better right now than the cars that I drove a decade ago. And 100 years from now, who knows how technology would look like. So if we see something that is, let's say, 1 billion years old technology, it would look like an approximation to God. It would do things that we can't even imagine. We would treat it just like a caveman treats a cell phone. A caveman looks at a cell phone and says, well, I've seen rocks of all types. This is a very special rock. You know, it's very shiny. That's what some people said about Oumuamua, for example. There might be a lot of traffic out there in interstellar space. And we just don't know. Because starshot-like probes would not be recognized by existing telescopes. We won't see them. They're too small. Our telescopes cannot see such things. So they might be out there, but we just don't know. And you know, civilizations might send out these things to places that have most resources. For example, clusters of galaxies. You know, the universe is expanding, but it's not just expanding. Its expansion is accelerating with time. So in fact, everything that we see away from the Milky Way galaxy, other galaxies, eventually will run away from us at a speed larger than the speed of light. We would never be able to chase those other galaxies, and we will be left in our own galaxy. So if you think about it and you want to maximize the amount of resources that you have in a distant future, then you want to be in the place where there is the most resources. And a cluster of galaxies represents that. It has typically 1,000 galaxies in it. So that's the place you want to migrate into. It's just like migration of civilizations to banks of rivers, you know, in the ancient times. And so the same thing might happen in the universe. We just don't know if it happens right now. Now, Enrico Fermi is a very famous physicist. And he once had lunch with colleagues with his group. And they were talking about the search for extraterrestrial civilizations. And by the way, I should say that, you know, 80 years ago, this was a subject that was discussed by the most, you know, prominent minds. In fact, Winston Churchill in 1940 wrote an essay about the likelihood, the fact that it's very likely that extraterrestrial civilizations are out there. And that was just before he became prime minister. And then, of course, I mean, he didn't have time to publish that essay, but it was discovered. So Enrico Fermi discussed it with his research group. He was a very mainstream physicist. And then he said, wait, if it's likely that they are out there, where is everybody? Why don't we see them? And that remained as Fermi's paradox. And in my mind, the most likely explanation is they are short-lived. Once they develop the means of communication, they develop their technologies to the level that exceeds the technologies we have right now, they also develop the means for their own destruction. You may call it the Brexit factor. So it might well be that there were a lot of civilizations out there, but they are dead right now. But that doesn't mean that explains why we don't see signals from active civilizations if they are short-lived. But it doesn't mean that we can't search for relics that they left behind. In fact, the whole field of archaeology is based on that, right? You dig into the ground and you look for evidence for ancient cultures that do not exist anymore. And you can do the same thing in space. I call it space archaeology. So we can look for signatures of dead civilizations. We can search for burnt up surfaces of planets that went through a nuclear war. We can search for atmospheres that have industrial pollution. We can search for relics in the form of technological equipment that is flying through space that is dysfunctional, defunct, but represents a civilization that existed a while ago. And it doesn't need to be on other planets. These relics may be floating in space. So my hope is that this will serve as an important history lesson for us, because if we find evidence for dead civilizations and we can identify the reason that they are dead, be it due to a war or because they didn't take good care of their planet, some bad politics. Then it will teach us a lesson to get our act together and behave better so that we will not share the same fate. We can search for technological artifacts. So for example, if a planet passes in front of its star, we can examine the composition of the atmosphere. We can search for oxygen that may indicate primitive life, microbial life, but we can also search for industrial pollution. Now, industrial pollution could be intentional. If the planet was too cold to start with, you might want to cover it with a blanket of gases that are artificial that will warm it up. You can look for the reflectivity of photovoltaic cells that cover, for example, the permanent day side of PROXIMAB in order to generate electricity on the permanent night side of PROXIMAB. So you can look for the reflectivity of those photovoltaic cells. If there is a tidally locked planet, as the planet moves around the star, you would see the special signatures of an artificial coating like a photovoltaic cell, solar cell, which is very different than the reflectivity of vegetation. Vegetation has a so-called red edge. Leaves of trees, they reflect red light, infrared light, because it cannot be used for photosynthesis. They only consume ultraviolet radiation, optical radiation. It's used for photosynthesis. The infrared radiation is garbage, so it's being reflected. And when you look at our planet from a distance, you see evidence for a red edge, a high increase in reflectance at infrared radiation. If the planet was covered instead of by vegetation, if it was covered by photovoltaic cells, the reflectivity will change at a different wavelength. And you can look for that. Finally, I would like to mention this anecdote that, in fact, when you look at your wedding band, if it's made of gold, you might wonder, where did this gold come from? Well, we now know the answer. We figured the answer only a year ago. Astronomers figured it out. The LIGO experiment that detected gravitational waves for the first time a few years ago, and for which the Nobel Prize was awarded a few years ago, discovered the merger of two neutron stars. And the gravitational waves, the ripples in space-time that were generated as a result of the merger of two neutron stars, was followed by the emission of light. And from analyzing this light, astronomers were able to deduce that heavy elements, like the gold that we have in a wedding band, were most likely produced in such events. When two neutron stars collide, a little bit of the neutron matter is expelled into space, and then it decays, because it's not stable, it decays into heavy elements like gold and uranium, very heavy elements. So next time you look at a wedding band, remember that this material was produced as a result of a violent collision of two neutron stars, stars that weigh as much as the sun, roughly the size of Boston. That's where it came from. Now, both uranium and gold are the sources of evil here on Earth, right? So you might say, well, if there is a neutron star collision somewhere in the galaxy, planets that are close to that collision site will have a lot of gold and uranium. We better be careful because, you know, they might have a lot of nuclear weapons out there. One thing, of course, is that once you have too much gold, it's not worth much, you know. So, I mean, it's good to a limit to get more gold, but beyond a certain amount, the value will drop. So, anyway, things that we find as precious, rare elements, really are rare because we are relatively far from a site of a neutron star merger. Something to keep in mind. when we move around the galaxy, we might go to places that have more of these. And actually, molybdenum is another element produced in such collisions, and that's important for life. So my hope is, in summary, that if we ever venture into the galaxy, into interstellar space, we will see a lot of traffic out there, and we'll hear a message back saying, "Welcome to the Interstellar Club." Thank you.
Thank you for informing and kind of blowing my mind a little bit there.
I didn't intend to.
No, in a good way. So we have a few minutes left. We'll try and get through a couple of these, and then we do invite you to continue the conversation downstairs in the reception. But we're going to start. We're going to go a little deep. Given that life in other places might be similar or very different than life on Earth, how do you define what life is? Is there a gray area?
That's an excellent question. In fact, I wrote a textbook about extraterrestrial life, and the first, together with a former postdoc of mine, Manas Villingam, and the first question that we try to address is the definition of life. And of course, it's difficult to define it because all we can talk about is life as we know it, and there could be many other forms of life. Now, what do we mean? I mean, there are some characteristics of life that we are familiar with, that something that can reproduce itself, that can make copies, and that can maintain some activity. But we will know it when we see it. Okay, and we pretty much recognize what life is on Earth. So the idea is, if we see something unusual on the surface of another planet by visiting the surface, we could examine it well enough with our scientific tools to tell us if it's life. And the fundamental question is it life like we find here on Earth? If it looks just like the life we have here on Earth, it might be that there is only one path to life, one recipe in this cookbook. And the other possibility is that life was shared between the place that we visit and Earth. Both of these are fascinating. If we find life that is completely different than the DNA-based life that we find on Earth, then it would be remarkable, because that will open our eyes to a completely different path for life, for other recipes. And I'm sure there would be a lot of research on that. And I should say that all of this research on the origins of life could have important implications for medicine. Because when we understand life, we could develop ways to cure diseases and other issues with life. And so I think, like any other fundamental basic research, this path of exploration offers a lot of promise for the future.
Great. And so this next question ties, so obviously your comments when Oumuamua sort of hit the press, it went viral. I mean, it far surpassed just the astronomy community and even the science community. So if something artificial is discovered from interstellar space, what do you feel would be the best/safest way to tell us, the public?
Oh, I think we should immediately inform everyone. Frankly, when people talk about conspiracy theories, I don't think the government is that competent to keep a secret. And I think sharing information is the best approach in science, because different people can look at the same data and analyze it and figure out if it's real or not. In fact, Steven Spielberg got the honorary degree at Harvard, and after the ceremony, I shook his hand and I told him that we are searching for signals and things out there, and he said, if you do find evidence, please let me be the first to know about it. But of course, we will let everyone know about it.
Wouldn't the digital AIs produced by an intelligent civilization far outlive the civilizations themselves? So shouldn't we be looking for those?
Yes. In fact, I would think that we should be looking for the things that are longest lived, which are technological in origin. So we should look for equipment floating in space. That would be my natural. When we do our archaeological dig into space, I think we should think mostly about artificial equipment. The question is how to detect it. And I mentioned a few ways.
And for Starshot, aren't ground-based lasers hindered by the atmosphere? Wouldn't a space-based light source be better, such as focused sunlight or a space laser?
In principle, yes. The problem is that it costs a lot of money to lift things into space, and moreover, it's much more difficult to service them. As we know from our experience, that a telescope like the Hubble Space Telescope did cost us about, $10 billion. So, having a lot of lasers out there that weigh much more than a single space telescope would be too expensive to maintain. And so that's why we contemplated a station on the ground that is much more economic, that you can service and also maintain and make sure that all the optics is aligned. You can imagine robots doing it in space, but whenever we went through the numbers, it didn't look real.
Speaking of the cost, is exploration worth the enormous cost?
Oh, I definitely think so, because we're talking about the long-term future of our civilization. And, much of our activity, if you boil down your life, very often it has to do with your children. Just thinking about the next generation. That's true as an educator. For me, educating the young generation of today is extremely important. I have great faith that they would do greater things, they would think more clearly about the important priorities than our generation did, and that's my hope. And so when we always think about our kids, you can think long term. You can think about the kids of our kids and so forth, and what's the long-term future for our civilization? And if conditions deteriorate here on Earth, we should think big. We should think about going elsewhere. We should contemplate going into space, and that's obviously the place to go, because Earth, our life on Earth is on a two-dimensional surface. So most of the time when you open the newspaper, it talks about what happens on this two-dimensional surface. But there is a third dimension that carries a lot of information, a lot of space out there that we could explore, and why not? There is a lot of real estate out there.
Is sentience necessary for interstellar travel? Is there a mechanism by which a non-sentient species or civilization could travel?
Well, yes. Mother Nature itself produces spacecrafts that carry tiny astronauts. For example, we see on Earth rocks that came from Mars. How did they travel? Well, they originated from an asteroid impacting Mars and lifting the surface layer of rock from its surface and kicking it into space, and eventually some of these rocks landed here on Earth. And one of these rocks that was examined about 2 decades ago, when people at MIT studied the magnetic properties of that rock from Mars, they concluded that it was not heated by more than 40 degrees Celsius, or more than 104 degrees Fahrenheit, meaning that on its journey from the surface of Mars to Earth, life could have survived. And so potentially, if there was life on early Mars, it may have come to Earth. Perhaps it predated life on Earth. Perhaps we are all Martians. But it demonstrates an important principle, that nature is often capable of doing things that we imagine as being our ultimate technological goal, sending life into space on a spacecraft. Nature did it with rocks a long time ago, and we actually wrote a paper just recently that we just submitted for publication this week with my undergraduate students, showing that boulders that passed through the Earth's atmosphere could have been scooping life from the atmosphere of Earth and taking it out of the solar system. So if there were tiny astronauts in the atmosphere of the Earth in the form of microbes, they could have traveled through the solar system into interstellar space long before New Horizons was thought of.
And so this will be our last question for now. And again, please join us at the reception. Do you have any advice for students applying to college who are interested in joining the search for extraterrestrial life? And what are the best majors? We have a student group in here, I believe. So,
yes, definitely. I think it's an exciting frontier for the future, and the next generation may find the answer to many of the questions that I asked. And the most important advice that I would give is don't listen to the adults in the room. Just do what you think is right based on evidence, not on prejudice. Explore the unknown, go in directions that nobody dared to go. Because actually, it's, going on the road not taken is actually what's fun about life. And that would be my advice. Do that. And perhaps you will be the first to discover extraterrestrial life.
Thank you for being here. We thank all of you for being here as well. I believe there may or may not be a book being written
within a year
as we speak, right?
Yes.
Within a year. So you're here to hear first. Keep an eye out for that. We hope to see you back here soon. Please join us downstairs. Thank you.